What's up, guys? My name is Dream, and working with me is TJ. We wave to you from our homes. Speaking of waves, there are actually tons of waves around us all over the world, some that we can't even see. So, we don't just have this wave, we also have waves that are supported by science. In today's video, we'll be discussing the different types of waves. That includes longitudinal waves, transverse waves, and electromagnetic waves. So, let's get right into it. One type of wave is what we call the longitudinal waves. Longitudinal waves are waves that move at the same axis or are parallel to the source's direction, meaning that whatever direction the source of force is going, the waves react in that same direction. When you think of longitudinal waves, think of the latitude and longitude of the Earth. The focus is longitude. One good example of this to vividly understand longitudinal waves is when we play with slinkies. Slinkies can do other things, which include transverse waves, which we will talk about later. But slinkies can also make longitudinal waves. To create longitudinal waves, you just move the slinky forward and backward quickly. You will then see energy being transferred throughout the slinky, seeing a moving section of the slinky that is compacted together. This is an example of a longitudinal wave. As of right now, I'm given an example of a longitudinal wave. Sound waves is an example of a longitudinal wave. So from when I'm talking right now, to when I tap, to when I snap, to when I play this guitar, or to anything that makes any noise, some sort of noise at all, is an example of a longitudinal wave. Sound waves are a series of compacted and vibrating air molecules. So when we make noises, we're pushing the air, causing the air molecules to run into each other and crunch together. There are a repetitive amount of these compacted areas that propagate or spread apart that go into our ears, thus making us hear it. So those are two prime examples of longitudinal waves. The second type of wave are transverse waves. Transverse waves are waves that move toward a certain direction like the longitudinal waves, but propagate in a perpendicular or 90-degree angle. To simplify this term, the word transverse is similar to the word across. So they move on a different axis, meaning that they move up and down instead of forward and backwards. They still have a goal of moving in a certain direction, but also move differently compared to the longitudinal waves. TJ will explain to us some examples of transverse waves.
Water ripples are a great representation of transverse waves because it helps us visually understand a transverse wave's properties. Today, I have with us a clear tub of water, and as I disturb the water, watch closely at how the water reacts. The clear tub enables us to see a cross-section of the water ripples, and as I disturb it, and more we can see it form a transverse wave. This can be identified as a transverse wave because the ripples travel perpendicular to the direction of the propagation of the wave, in this case, horizontal, and it moves through the water, which can be considered the medium. The ripples oscillate up and down, thus forming a transverse wave. The rope, as we've observed, is the most common and easiest way to demonstrate transverse waves. Again, transverse waves travel perpendicular to the direction of the propagation of the wave, and the medium in this situation would be the rope. As Dream exerts force on the rope, moving in an up and down motion, we can momentarily see a transverse wave travel to the direction he is moving. Put simply, the wave travels horizontally because Dream moves vertically up and down. And while the properties of a transverse wave cannot be directly demonstrated, water ripples and a rope gives us a better visual understanding. Electromagnetic waves are created as a result of vibrations between an electric field and a magnetic field. In other words, electromagnetic fields are composed of oscillating magnetic and electric fields. These can include radio waves, microwaves, infrared, light, ultraviolet, X-rays, and gamma rays, which all make up the spectrum where higher frequency waves are dangerous and low frequency waves are safer. The visible light spectrum is a part of the electromagnetic spectrum that the human eye can see. Fun fact, the human eye can detect wavelengths from 380 to 700 nanometers. The visible light spectrum is usually defined as having wavelengths in the range 400 to 700 nanometers, or between the infrared waves and ultraviolet waves. Examples of visible light often come from light bulbs, candles, as well as television, computer screens, glow sticks, and fireworks. As you can see, we are outside to bask in the glory of the sun, an example of a visible light source. The color of an object we see is actually the color of the light reflected, as all other colors are absorbed.
Overall, waves come in many different shapes and sizes. They also can be differentiated by either perpendicular or parallel motion. You can also differentiate between electromagnetic waves by their frequencies. All in all, waves are an important aspect of science and our everyday lives. And that's it, folks. I hope you got a good overall summary of the different types of waves we encounter. Please continue to be safe out there. Continue to be optimistic by sending good energy towards each other by waving hello and goodbye. You see what I did there? Anyways, until next time, peace.